The Amazon at ground level is not quiet in the way people imagine silence. Even when birds pause their calls and the canopy seems still, the forest continues speaking through other channels, through insects moving in leaf litter, through moisture dripping from vines, through the constant chemical exchange between living organisms. The air is warm and heavy with humidity, a dense medium that holds scent close to the earth, rather than letting it disperse quickly. Every animal moving through this environment leaves behind a trail of invisible information. Oils from skin and fur, crushed vegetation releasing plant compounds, tiny fragments of tissue, sweat, urine, and sometimes blood. In a place where sight lines are limited by walls of foliage, these chemical signals become the most reliable map of recent activity. For the jaguar, the largest cat in the Americas and one of the Amazon's most capable predators, this invisible map is as meaningful as tracks in soft mud. A jaguar rarely needs to rush. Unlike pursuit predators that rely on endurance and speed across open terrain, jaguars evolved for a world of dense vegetation and short distances. Their bodies are compact but immensely powerful, built for explosive bursts rather than long chases. Their shoulders and forelimbs are heavily muscled to control prey at close range, and their jaws deliver one of the most formidable bites among big cats. Jaguars frequently kill with a technique unusual in the cat family, piercing directly through the skull of their prey. Yet the moment of attack, the violence people imagine when they think of a predator, is only the final seconds of a much longer process. Long before the jaguar commits to an ambush, it has already interpreted a complex network of clues left behind in the forest. Territorial mammals communicate extensively through scent, and jaguars are no exception. Individuals patrol enormous territories, often covering dozens or even hundreds of square kilometers, depending on prey availability and habitat structure. Within these areas, they deposit scent marks using urine sprays, feces, and glandular secretions that carry highly specific chemical information. These marks announce identity, reproductive status, and recent presence to other jaguars moving through the same region. The forest floor becomes a chemical bulletin board. Another cat, passing hours later, can determine whether the scent came from a dominant male, a female in estrus, or a transient animal moving through unfamiliar ground. Prey species also live inside this chemical conversation. White-lipped peccaries, capybaras, deer, and tapirs constantly sample the air and ground for the faint musk of predators. When that scent appears, feeding behavior changes immediately. Animals lift their heads, freeze, and reposition themselves within the group. What seems like sudden tension spreading through a herd is often the response to an odor humans cannot perceive. In dense rainforest, smell travels around obstacles that vision cannot penetrate. The forest warns its inhabitants long before the predator is visible. For the jaguar, scent functions not only as communication, but also as investigation. The nasal cavity of a big cat contains millions of olfactory receptors capable of detecting minute concentrations of airborne molecules. When a jaguar encounters a particularly interesting scent, it may pause and perform the flamen response, curling its upper lip to expose specialized receptors within the vomeronasal organ on the roof of the mouth. This structure allows mammals to analyze complex chemical signals, particularly those associated with bodily fluids. Urine, reproductive pheromones, and blood all carry detailed biological information that animals can decode through this system. Blood is where the story becomes more intense. When an animal is injured, the chemistry of its environment changes immediately. Blood contains iron-rich compounds and volatile organic molecules that disperse rapidly through warm air. At the same time, damaged tissue releases metabolic byproducts associated with stress and inflammation. Even a minor wound begins producing a plume of scent that spreads outward and settles onto surrounding surfaces. Leaves brushed by the animal collect tiny droplets. Soil absorbs diluted traces as the animal passes. Broken stems and crushed vegetation release plant chemicals that mix with the metallic odor of blood. Within minutes, the forest floor becomes a layered record of what happened. The jaguar does not behave like a dog tracing a single line of scent along the ground. Instead, it interprets the broader pattern created by these signals. The cat may encounter a disturbed patch of vegetation where the smell of prey mixes with blood and sweat. Rather than following each step precisely, it reads direction, intensity, and timing. Fresh scent is sharp and strong, older scent duller and fragmented. By sampling the air repeatedly and examining disturbed ground, the jaguar constructs a mental picture of movement. It knows where the animal passed, how recently it moved through the area, and whether its pace suggested calm travel or panic. Panic is particularly revealing. Animals fleeing injury rarely move efficiently. They crash through dense undergrowth, break branches, and pause frequently to rest. Each stop allows scent to accumulate in one location, strengthening the chemical signal. Droplets of blood fall onto leaves and soil, forming a breadcrumb trail detectable by multiple species. Flies often arrive first, drawn by the smell within minutes. Their presence attracts insect-eating birds that begin scanning the forest floor. Even scavengers may begin investigating long before the wounded animal collapses. To a jaguar moving quietly through this environment, these signals form a trail of probability rather than certainty. The predator does not know exactly where the injured animal is, but it knows the animal is nearby and struggling. The cat moves slowly downwind of the scent plume, minimizing the chance that its own odor will alert the prey. Every few meters, it pauses, listening. Jaguars possess excellent hearing and low-light vision, adaptations that allow them to detect subtle motion in shadowed understory. If the injured animal is within range, the predator's final approach becomes almost silent. Yet the significance of scent in the Amazon extends beyond predator and prey. Humans entering this ecosystem participate in the same chemical exchange, whether they realize it or not. Walking through the forest releases plant oils from crushed leaves. Skin sheds microscopic cells that settle onto the ground. Sweat carries salts and organic compounds that accumulate on clothing and gear. Even calm breathing releases carbon dioxide and moisture detectable by insects and other animals. When stress enters the situation, these signals intensify. Fear triggers adrenaline, which increases heart rate and perspiration. Movement becomes faster and less controlled. Branches snap under hurried footsteps, vegetation is pushed aside, and scent trails grow stronger. If a person is injured even slightly, the presence of blood introduces the same chemical signal that predators associate with wounded prey. The forest does not categorize scent according to human expectations. It registers only information. This does not mean a jaguar automatically begins hunting a human who is bleeding. Jaguars generally avoid people and prefer prey that fits within their normal diet. However, the same ecological system that guides predators toward vulnerable animals also responds to any strong biological signal. Blood, sweat, and erratic movement broadcast a story about vulnerability into a landscape filled with organisms evolved to read such stories. That is the deeper reality behind the idea of scent in the Amazon. You are never simply a body moving through empty space. Every step writes chemical information across leaves, soil, and humid air. Animals capable of interpreting those signals do not need to see you immediately to know you are there. Long before visual contact occurs, the forest has already recorded where you passed, how quickly you moved, and whether something about your behavior suggests weakness. The jaguar lives comfortably within that invisible record. It does not need to chase blindly through the jungle searching for prey. Instead, it moves through a world of scents that describe the recent past in extraordinary detail. When blood enters the equation, that story becomes louder, clearer, and far easier to read. The deeper forest floor of the Amazon feels different from the upper canopy world. Light reaches it reluctantly, filtered through dozens of meters of leaves until only a dim green glow remains. Down here the air is cooler, heavier, and almost motionless. The ground itself is soft with decomposition, layered with years of fallen leaves, bark fragments, fungal threads, and the dark soil created by endless cycles of decay. Every step sinks slightly, releasing the faint smell of rot and plant oils. Movement in this environment rarely goes unnoticed, not because the forest is watching in a conscious sense, but because every disturbance changes the delicate structure of the leaf litter. A bent stem, a displaced leaf, a patch of compressed soil, each alteration becomes part of a temporary trail written into the landscape. When an animal is injured and moving through this environment, the disturbance multiplies. The forest floor becomes a corridor of subtle damage. Leaves flip over, exposing their pale undersides. Twigs snap under uneven steps. Droplets of blood fall and soak into the organic debris, adding a metallic scent to the chemical mixture already rising from the soil. For mammals like jaguars, these signals can be interpreted directly through smell and observation. But even for animals that do not track prey through scent in the same way, a wounded trail changes the ecosystem around it. Insects are often the first to respond. Flies detect blood and exposed tissue with astonishing speed, sometimes appearing within minutes in humid tropical forests. Their presence draws attention from insect-eating birds and small reptiles that hunt them. Scavengers begin investigating the disturbed corridor. Prey animals passing nearby become nervous, detecting the scent of injury and predator activity in the same location. The entire stretch of forest begins to feel slightly different, more tense, more active, more unpredictable. What started as a single wounded animal now becomes a small ecological disturbance moving slowly across the forest floor. Within this subtle chaos lies an environment perfectly suited for one of the Amazon's most formidable ambush predators, the bushmaster snake, Lachesis muta. The bushmaster is the longest venomous snake in the Americas, capable of exceeding 3 meters in length, though its presence rarely announces itself through size alone. Its body is patterned in a complex arrangement of browns, tans, and black geometric shapes that match the texture of decaying leaves with uncanny precision. Even at close distance, the animal can disappear into the substrate. What makes the bushmaster unsettling is not speed or aggression, but stillness. It is a predator that succeeds by becoming indistinguishable from the ground. Unlike mammalian hunters, The bushmaster does not pursue prey over long distances. It relies on ambush. This strategy is supported by an extraordinary set of sensory adaptations. Along the snake's head, between the eyes and nostrils, lie specialized organs known as pit sensors. These pits detect infrared radiation, allowing the snake to perceive heat differences in its surroundings. To a bushmaster resting in leaf litter, the forest does not appear as a flat visual scene, but as a layered thermal landscape. Warm-bodied animals moving through the cool background of soil and leaves stand out clearly, even in near darkness. Yet heat detection alone does not determine where a bushmaster waits. Ambush predators must choose locations where prey is likely to pass. In tropical forests, animals often move along natural corridors created by terrain, vegetation density, or repeated use. Game trails, fallen logs, stream edges, and gaps in thick undergrowth all become predictable routes. The bushmaster positions itself along these pathways, remaining motionless for hours or even days. Its metabolism allows long periods of inactivity, conserving energy while waiting for an opportunity. This is where the disturbance created by a wounded trail becomes significant. When blood, panic, and uneven movement create a corridor of activity, the surrounding forest begins to react. Small animals investigate. Insects gather. Birds shift their feeding patterns. Even mammals that would normally avoid the area may pass through cautiously to assess the disturbance. Each of these responses increases movement through the same narrow strip of ground. The corridor becomes busier than usual, not because any single predator is intentionally guiding events, but because biological signals attract attention. For an ambush predator already occupying that terrain, increased traffic improves the odds of an encounter. The bushmaster does not need to smell blood from kilometers away or deliberately follow a trail like a mammal. Instead, it benefits from being exactly where the disturbance leads. Imagine the wounded path of a small mammal weaving through leaf litter. As it struggles forward, it unintentionally clears a slightly more open route through the debris. Leaves shift aside, stems break, and the animal tends to follow the easiest path through dense ground cover. The same path then becomes easier for other animals to follow as well. The result is a narrow track of compressed vegetation that temporarily guides movement. If that path crosses the location where a bushmaster is resting, the outcome becomes dangerously predictable. The snake's ambush strike is astonishingly fast. When a warm-bodied animal enters range, the bushmaster launches forward with a powerful extension of its body, delivering long, hinged fangs deep into tissue. Its venom is primarily hemotoxic, affecting blood clotting and causing severe tissue damage. Unlike some vipers that strike once and retreat, bushmasters are known to deliver multiple strikes if threatened or engaged, injecting significant amounts of venom in the process. In the dense forest where medical help may be hours or days away, such an encounter can quickly become life-threatening. Yet the bushmaster's true advantage lies not in aggression, but in invisibility. Field researchers studying these snakes often report how difficult they are to detect, even when actively searching. The triangular head blends seamlessly into the mosaic of leaves. The body's ridged scales mimic the irregular edges of plant debris. Only the faint outline of coils reveals that the ground itself is alive. A person walking through the forest may step within a meter of a bushmaster without ever noticing it. This is why the presence of disturbance matters. When an animal or a person moves calmly through the forest, steps tend to be deliberate. Careful movement reduces noise and vibration, allowing time to notice unusual shapes or patterns on the ground. Panic changes that behavior. A wounded or frightened animal moves erratically, pushing through vegetation instead of navigating around it. Footsteps become heavier and less controlled. Attention focuses forward toward escape rather than downward toward the ground. In those moments, the forest becomes harder to read. The Bushmaster does not need to track anything. It simply occupies a place where movement is likely. If the wounded corridor intersects with that place, the snake becomes an obstacle hidden within the system. This is the subtle but powerful reality behind many encounters between humans and ambush predators. The snake is not actively hunting the person. It is simply positioned along a path where unpredictable movement increases the chance of contact. There is also a deeper ecological irony here. The blood trail that attracts insects and scavengers may indirectly increase the activity of animals that bushmasters normally prey upon. Rodents investigating insects, small birds searching disturbed soil, and lizards chasing flies all become potential meals. The wounded corridor becomes a temporary feeding opportunity for multiple species simultaneously. In this sense, the disturbance created by injury reshapes the local food web for a short time. For the Bushmaster, patience turns that chaos into advantage. The Amazon often feels mysterious because many of its dangers operate through probability rather than pursuit. Predators do not always chase their prey across dramatic landscapes. Sometimes they simply exist within environments where vulnerable movement becomes predictable. The forest floor is a mosaic of hidden risks and opportunities, and animals that master stillness gain a remarkable advantage. What makes the Bushmaster particularly unsettling is that it embodies this principle perfectly. It does not need to stalk, roar, or announce itself. It only needs to remain exactly where it belongs, within the leaf litter of a forest, where every disturbance eventually guides movement through the same narrow spaces. And when the forest itself has already marked your path with noise, scent, and damage, the odds of crossing something silent rise quietly with every step. The rivers of the Amazon do not always look dangerous. In many places, the surface appears calm, dark, and almost reflective, as if the water itself were absorbing the jungle around it. Blackwater rivers in particular carry this illusion. Their color comes from tannins released by decaying vegetation upstream, staining the water a deep tea-like brown that blocks visibility almost completely. Even in daylight, objects disappear beneath the surface within a meter or two. Beneath that thin layer of reflected sky lies an environment where vision becomes nearly useless, and animals must rely on other senses to survive. In this world, the river is not primarily a visual habitat. It is a field of vibrations, electrical signals, and subtle chemical traces drifting through slow currents. Every creature that enters the water becomes part of that sensory landscape. Fish beating their tails generate pressure waves that ripple outward in all directions. Tiny crustaceans flick their appendages, producing vibrations detectable by predators equipped to sense them. Even the quiet movement of a turtle gliding along the riverbed creates disturbances in the surrounding water. These signals travel far more efficiently through liquid than through air, allowing animals to detect activity beyond the range of sight. Among the most extraordinary inhabitants of this hidden environment is the electric eel, a fish that has transformed electricity itself into a biological weapon. Despite the name, electric eels are not true eels, but a type of knife fish belonging to the genus Electrophorus. Their bodies are long and cylindrical, often exceeding 2 meters in length, and the majority of that body is not muscle but specialized electric organs. These organs are composed of thousands of modified cells known as electrocytes, arranged like stacked batteries along the length of the fish. When activated together, they produce powerful electric discharges capable of reaching hundreds of volts. This ability gives the electric eel a hunting strategy unlike almost any other predator in the Amazon. Instead of relying on speed or sharp teeth alone, the eel weaponizes the physics of electricity within water. Because water conducts electrical current efficiently, a discharge spreads rapidly outward from the eel's body. Any nearby animal becomes part of that electrical circuit, and the shock can instantly overwhelm its nervous system. Yet the eel does not rely solely on high-voltage attacks. Most of the time, it emits much weaker electric pulses that function as a sensory system. These low-voltage discharges create a constantly changing electric field around the eel's body. Objects in the water, including plants, rocks, and animals, distort that field slightly as electricity flows around them. Specialized receptors along the eel's skin detect these distortions, allowing the fish to form a kind of electrical image of its surroundings. In murky black water where sight fails, this system provides an astonishing level of awareness. Through this process, the eel can detect even subtle movements made by nearby animals. A small fish flicking its tail alters the electrical field in a distinctive pattern. A crustacean crawling along the riverbed produces another pattern entirely. The eel interprets these disturbances much the way a bat interprets echoes from sonar. The river becomes a three-dimensional map of electrical signals, constantly shifting as animals move through it. When prey enters this field, the eel's behavior changes dramatically. Researchers observing electric eels in the wild and in laboratory conditions have discovered that the fish often begins by emitting rapid bursts of high-frequency pulses. These pulses are not strong enough to stun prey outright, but they interact directly with the nervous systems of nearby animals. The electrical signal can trigger involuntary muscle contractions, causing hidden prey to twitch or move suddenly. That movement reveals their exact location within the dark water. Once the eel identifies its target, the attack becomes immediate and decisive. The fish curls its body around the prey, positioning both its head and tail close to the victim. By doing so, it effectively surrounds the animal with electric organs, maximizing the voltage passing through the target. A powerful discharge follows, flooding the prey's nervous system with electrical current. Muscles seize, coordination collapses, and the prey becomes momentarily helpless. In clear water, a healthy animal might attempt to escape before the eel can close the distance. But black water environments rarely offer that advantage. Vision is limited, obstacles are numerous, and the eel's electrical senses remain active even in total darkness. Once the fish begins targeting a struggling animal, the encounter often ends quickly. This is where injury becomes particularly dangerous. When a wounded animal enters dark Amazon water, it carries with it several forms of signal simultaneously. Blood releases chemical compounds that diffuse slowly through the current. Panicked swimming produces strong pressure waves detectable by predators sensitive to vibration. And perhaps most important, an injured body begins to lose control of its own muscles. Movement becomes uneven and inefficient as fatigue and pain disrupt coordination. For an electric eel, that combination of signals creates ideal conditions for hunting. The eel does not need to smell blood in the same way a mammal interprets scent trails. Instead, it benefits from the cascade of physical effects that follow injury. A struggling fish sends erratic bursts of movement through the water, constantly shifting the electric field around it. Each twitch becomes a beacon within the eel's sensory system. The eel closes in, emitting probing pulses that force the prey's muscles to respond involuntarily. With every electrical probe, the prey's location becomes clearer. Blackwater rivers amplify this vulnerability because the environment itself removes many escape options. Visibility remains poor for both predator and prey, but the eel compensates through electricity while the injured animal cannot. Roots from flooded trees form dense underwater tangles. Fallen branches create obstacles that slow movement. Silt clouds stirred by panic reduce visibility even further. In such conditions, efficient navigation becomes difficult even for healthy animals. For one already bleeding or disoriented, the river becomes a maze. Electric eels often patrol quiet stretches of these waters, particularly areas rich in fish or amphibians. Flooded forests during the rainy season provide an ideal hunting ground. As water spreads across the forest floor, fish move between submerged roots and branches searching for food. The eel glides slowly through these submerged corridors, its body producing faint electrical pulses that probe the environment ahead. When a wounded animal thrashes nearby, the signal is unmistakable. The eel's electric field begins to flicker with distortions as the prey moves through it. The predator angles its body toward the disturbance, its long anal fin rippling gently to maintain precise control of position. Another burst of pulses triggers sudden muscle spasms in the prey, confirming its location. Then comes the strike. The eel curls, discharges, and the water itself becomes the weapon. From a biological perspective, this strategy reveals something remarkable about evolution in dark aquatic environments. Instead of improving eyesight or speed, the electric eel developed an entirely new sensory modality and weapon system. Electricity allows the fish to hunt in conditions where most predators would be blind. It also enables a form of control over prey that bypasses physical struggle entirely. The eel does not overpower its prey through strength alone. It hijacks the animal's nervous system. This mechanism becomes especially effective when the target is already compromised. Injury introduces unpredictability into the prey's movements. Muscles misfire. Swimming patterns collapse into chaotic bursts of energy followed by exhaustion. In water where electricity travels freely, these spasms become exactly the kind of signal the eel exploits. The unsettling truth is that once an animal begins to lose control of its body in dark Amazon water, it does not need to be actively tracked by scent to become vulnerable. The environment itself broadcasts the signs of weakness through multiple channels. Vibrations spread through the water column. Electrical disturbances ripple through the eel's sensory field. Chemical traces drift slowly through the current. Some predators interpret smell. Others interpret motion. The electric eel interprets electricity. And in the silent darkness of blackwater rivers, that may be the most revealing signal of all. On the floor of the Amazon rainforest, scale becomes deceptive. The towering canopy above may dominate the imagination, with its massive trees, broad leaves, and the distant calls of birds and monkeys echoing through green light. Yet the true engine of the rainforest often operates at a far smaller level. Beneath the fallen leaves and tangled roots exists a dense micro-world of insects, arachnids, fungi, bacteria, and other tiny organisms that collectively shape the ecology of the forest. Every square meter of ground hosts an astonishing number of species, each adapted to read subtle signals in the environment that larger animals rarely notice. In this lower layer of the ecosystem, biological information spreads quickly and rarely goes unused. A crushed leaf releases plant chemicals that attract herbivores and their predators. The scent of nectar drifting through humid air guides pollinating insects to hidden flowers. Even the faint chemical traces left by a passing caterpillar can draw parasitoid wasps that specialize in finding their hosts by smell alone. To the human observer, the forest floor may appear quiet and uniform, but to the small creatures living within it, the ground is alive with invisible messages. When blood or exposed tissue enters this system, the signal spreads rapidly. Proteins, salts, and organic molecules seep into the surrounding soil and leaf litter. Tiny droplets may cling to the rough surfaces of bark or leaves, slowly evaporating and releasing chemical cues into the air. For organisms equipped with sensitive antennae and specialized receptors, these cues function almost like a broadcast. They do not need to travel far to become meaningful. At the scale of insects, a few centimeters can represent an entire landscape. Among the many arthropods that exploit this network of signals is the assassin bug, a member of the family Reduviidae. These insects are widely distributed across tropical ecosystems and include hundreds of species, many of which specialize in ambush predation. Their name reflects their method of hunting, a sudden, precise attack delivered with a specialized mouthpart known as a rostrum. This elongated, needle-like structure functions as both a piercing tool and a feeding tube. Once inserted into prey, it delivers digestive enzymes that rapidly immobilize and liquefy internal tissues. The assassin bug then feeds by drawing the nutrient-rich fluid back through the same structure. The mechanics of this feeding strategy require accuracy. Assassin bugs do not possess the speed or strength of larger predators. Their success depends on proximity and timing. Most species rely on camouflage, patience, and acute sensory awareness to detect suitable prey within striking distance. Their bodies are often textured and colored to resemble twigs, bark fragments, or dried plant debris. When motionless, they blend almost perfectly with the forest substrate. This camouflage works best in the cluttered environment of the rainforest floor, where shapes overlap and shadows soften the outlines of objects. A twig lying among leaf litter might actually be an insect waiting for an opportunity. For prey animals moving through this environment, distinguishing between living predator and harmless debris becomes extremely difficult. Yet, assassin bugs are not merely passive observers of movement. They are also sensitive to chemical signals drifting through their immediate surroundings. Like many insects, they possess antennae equipped with receptors capable of detecting a wide range of organic compounds. These receptors allow them to interpret chemical cues associated with prey activity, damaged plants, and biological fluids. The scale of detection is small, centimeters rather than meters, but in the crowded microhabitat of the forest floor, that distance is often enough. Consider what happens when an injured insect or small vertebrate passes through leaf litter. A torn wing, punctured exoskeleton, or small drop of blood introduces proteins and volatile compounds into the surrounding air. Other insects quickly begin to respond. Flies arrive to investigate. Ants detect the scent and begin recruiting nestmates through pheromone trails. Predatory beetles and spiders may also approach, drawn by the promise of weakened prey. The assassin bug occupies a unique position within this miniature cascade of attention. It does not need to chase the injured animal across the forest floor. Instead, it benefits from the increased traffic created by the disturbance. Prey species investigating the scent may wander within reach of the hidden predator. Small insects attracted to exposed fluids become targets themselves. Even the subtle vibrations created by struggling prey can alert the assassin bug that something nearby is worth investigating. At close range, the bug's hunting behavior becomes remarkably precise. When prey enters striking distance, the insect lunges forward with sudden speed, driving the rostrum into the victim's body. The injection of digestive enzymes begins almost immediately. These enzymes break down tissues and interfere with normal physiological processes, immobilizing the prey while simultaneously converting its internal structure into a liquid meal. For many insects, this attack is fatal within seconds. Some assassin bug species exhibit even more unusual strategies. Certain tropical varieties coat their bodies with dust, plant fragments, or the remains of previous prey, enhancing their camouflage and masking their scent. Others position themselves along narrow pathways used by ants or other insects, intercepting individuals as they pass. The diversity of these tactics illustrates a broader principle in rainforest ecology. Predators evolve to exploit the smallest patterns of movement and chemical signaling. In this context, exposed biological fluids become particularly significant. Blood or tissue fluid represents a concentrated source of nutrients, but it also functions as a signal that something nearby has been injured. Insects capable of detecting these signals gain an advantage because weakened animals often move slowly and unpredictably. Even a brief pause while grooming a wound or struggling to recover can create the stillness an ambush predator requires. For humans, the presence of such tiny hunters rarely inspires the same fear associated with large animals like jaguars or snakes. Yet, assassin bugs introduce a different kind of discomfort. Some species are capable of delivering painful defensive bites if handled or pressed against skin. The bite itself occurs when the rostrum penetrates human tissue in the same way it would pierce insect prey. While most encounters are accidental, the experience can be surprisingly intense. The discomfort comes not only from the pain, but from the realization of how close the insect must be before it is noticed. Unlike large predators that announce themselves through sound or movement, assassin bugs operate at a scale where detection often happens too late. The insect may have been present on a leaf or branch all along, perfectly still, interpreting the surrounding chemical environment long before the human observer becomes aware of it. This subtlety reveals an important truth about the rainforest. Biological information rarely belongs exclusively to one species. When blood enters the environment, it does not remain a private signal between predator and prey. It spreads outward through the ecological network, becoming available to any organism capable of detecting it. Ants, flies, beetles, spiders, and predatory insects all respond in their own ways, each interpreting the signal according to their evolutionary needs. The assassin bug represents one of the most surgical responses within that network. It does not rely on strength, speed, or dramatic pursuit. Instead, it waits within the dense fabric of the forest floor, reading chemical cues that indicate opportunity. When prey arrives within reach, whether drawn by scent, weakened by injury, or simply moving through the wrong patch of leaf litter, the predator acts with precision. This perspective challenges the common assumption that the Amazon's most dangerous interactions must involve large animals. In reality, much of the rainforest's predatory activity unfolds at scales too small to notice easily. Countless miniature encounters occur every minute among insects and other arthropods, each shaped by chemical signals drifting through soil and air. What makes the assassin bug unsettling is how perfectly it embodies this principle. The insect does not need the drama of a chase or the intimidation of size. Its entire strategy depends on reading the quiet language of biological residue and responding faster than its prey can react. And in a rainforest where blood rarely remains unnoticed, even the smallest hunter can become part of the story once the forest begins to read the signals you leave behind. The rivers of the Amazon feel open compared to the forest. Light reaches the water more easily than the tangled understory, and the current constantly reshapes the surface into ripples, reflections, and shifting shadows. But openness here does not mean emptiness. A river in the Amazon is one of the most monitored environments in the entire ecosystem. Everything moving through it leaves a trace that travels far beyond the point where the disturbance first occurred. Silt clouds drift downstream. Vibrations move through water faster than through air. Oils from skin or fish scales spread in thin films across the surface. Even subtle chemical changes disperse along currents and eddies, creating a flowing map of recent events. Unlike the forest floor, where scent clings to leaves and soil, the river carries information outward. A disturbance rarely stays local for long. The wake of a struggling fish can ripple dozens of meters across still water. Blood released from a wound dissolves into microscopic particles that drift with the current, mixing with organic debris and suspended sediment. To animals living in the river system, these signals form a constantly changing network of clues. A quiet stretch of water can suddenly become busy with meaning. Few animals read this watery landscape as effectively as the giant otter, Pteronura brasiliensis. These animals are among the largest members of the weasel family, reaching nearly 2 meters in length when the muscular tail is included. Yet their physical size tells only part of the story. Giant otters are not solitary hunters quietly slipping through the water like their smaller relatives. They are intensely social mammals that live in cohesive family groups, often consisting of a breeding pair and several generations of offspring. Within their territory, they function less like individual predators and more like a coordinated surveillance system. Each group occupies a defined stretch of river, lake edge, or flooded forest channel. These territories are not vague ranges, but actively maintained zones of control. Giant otters mark their boundaries with scent produced by glands near the base of the tail, leaving strong musky signals on rocks, sandbanks, and exposed roots along the shoreline. These scent marks communicate ownership to neighboring groups, reducing the likelihood of constant physical conflict. But scent alone is not the only mechanism maintaining order. Giant otters patrol their waterways frequently, traveling along predictable routes while scanning the environment with sharp vision and acute hearing. This constant patrol creates a remarkable level of environmental awareness. Members of a group move through the water with their heads raised, eyes and nostrils just above the surface. From this vantage point, they observe movement along the banks, detect splashes that indicate fish activity, and listen for unusual sounds. Giant otters are also highly vocal animals. Their calls range from soft contact chirps between family members to loud explosive barks that echo across the river when a threat is detected. These vocalizations act as a communication network, allowing individuals spread across dozens of meters of water to respond quickly to disturbances. In this environment, evidence travels differently than it does in the forest. A wounded animal moving through leaf litter leaves a corridor of broken plants and scent that slowly fades with time. In water, the same event spreads outward like a signal flare. Imagine a fish attacked by a predator near the surface. Its scales scatter into the water, reflecting light as they drift downward. The fish thrashes violently, creating sharp splashes that echo across the river channel. Blood diffuses into the current, forming faint chemical trails that extend downstream. Within moments, the entire stretch of water carries the signature of distress. For giant otters, such signals are impossible to ignore. Fish form the core of the giant otter diet, and the animals are highly efficient hunters. Their long, streamlined bodies allow them to pursue prey underwater with speed and agility, while powerful jaws and sharp teeth make quick work of slippery catches. Hunting often occurs cooperatively, with multiple otters diving repeatedly through schools of fish, creating bursts of turbulence that herd prey into tight clusters. When fish panic under this pressure, they often break the surface, revealing their location to the hunters above. Because of this feeding strategy, giant otters become extremely attuned to the sounds and movements associated with struggling fish. A sudden splash may indicate an easy meal. A cluster of nervous ripples could signal prey hiding among submerged branches. The animals constantly interpret these cues while patrolling their territory. In calm conditions, even a single disturbance can draw attention. Now imagine that disturbance occurring close to a giant otter den or hunting corridor. Giant otter dens are often located in eroded riverbanks where tunnels extend from the water into soft soil. Nearby, the animals maintain cleared areas known as latrines and grooming sites. These open patches allow them to leave scent marks and maintain visibility along the shoreline. Because the group uses these locations repeatedly, they become central points in the otter's mental map of the territory. Activity near these areas is quickly noticed. When unfamiliar movement enters this space, whether from another predator, a boat, or an injured animal, the otters respond immediately. Heads rise above the water. Bodies orient toward the disturbance. Loud alarm barks ripple through the group as individuals converge on the source. The response is rarely subtle. Giant otters are bold animals, and their confidence comes from numbers. A coordinated group moving quickly across the water can appear surprisingly large and intimidating. Blood in water intensifies this reaction. The scent itself is only one part of the signal. Blood often accompanies frantic splashing, sudden changes in fish behavior, and unusual patterns of movement along the river surface. These combined cues suggest an active event unfolding within the territory. For animals already monitoring the river with constant vigilance, such signals trigger investigation almost automatically. This investigation does not necessarily mean the otters intend to attack. In many cases, they simply approach to identify the source of disturbance. Yet their behavior during these encounters can feel confrontational. Giant otters often swim directly toward intruders, raising their heads high and vocalizing loudly. The group spreads slightly across the water, forming a loose line that blocks movement along the river. Their teeth are visible, their voices sharp and repetitive. The message is unmistakable. This section of water is already occupied. Their reputation among researchers and river communities reflects this intensity. While attacks on humans are extremely rare, giant otters have been known to defend their territory aggressively when they feel cornered or when young pups are present. Their size, intelligence, and coordination make them formidable opponents in close quarters. A full-grown giant otter weighs more than 30 kilograms and possesses jaws designed to crush fish bones. Several adults responding together create an overwhelming display of force. What makes these encounters particularly interesting from an ecological perspective is how they illustrate a different type of tracking. Jaguars interpret scent trails left behind in vegetation. Bushmasters wait silently where movement becomes predictable. Giant otters, by contrast, monitor an entire river system simultaneously through sound, smell, and group awareness. The scent they respond to is not limited to chemical odor alone. It includes splashes, vibrations, drifting particles, and the behavior of other animals reacting to disturbance. In this sense, a river functions almost like a shared information highway. Evidence spreads quickly, and intelligent social predators can intercept it long before the original source arrives. A wounded fish drifting downstream, a panicked animal thrashing near the bank, or even the metallic scent of blood mixing with warm water can signal that something unusual is happening within the territory. The giant otter group responds not as isolated individuals, but as a coordinated unit. One otter notices movement. Another hears the alarm call and approaches. A third surfaces near the bank to scan for additional threats. Within seconds, the family gathers, their collective awareness covering a wide area of water and shoreline. What began as a small disturbance now triggers a rapid and organized reaction. This is why rivers in the Amazon can feel deceptively calm. The surface may appear quiet, reflecting green walls of forest on either side. But beneath that stillness lies an intricate system of signals constantly traveling through the water. Animals like giant otters read those signals with extraordinary sensitivity, transforming small clues into coordinated responses. And when blood enters that system, when panic, movement, and chemical traces spread across territory lines, the river does not simply carry the evidence away. It broadcasts it. In many parts of the Amazon, the water looks almost peaceful. Wide rivers drift slowly between walls of forest, their surfaces reflecting broken patches of sky and the leaning silhouettes of trees. From above, it can be difficult to imagine that anything dangerous lives beneath such calm water. The current moves lazily around submerged branches. Dragonflies skim the surface, and small fish occasionally break the water in quick flashes of silver. Yet this quiet appearance hides an environment where information spreads with unusual speed. In rivers and floodplains, signals do not stay where they originate. Movement, vibration, and chemical traces travel outward through the water column, creating ripples of awareness that extend far beyond the moment that produced them. Among the animals most closely associated with this process are the piranhas, a group of South American fish belonging primarily to the genus Pygocentrus and several related genera within the Serrasalmid family. Popular imagination often exaggerates their behavior, portraying them as relentless predators that reduce anything entering the water to bones within seconds. The reality is more complex and, in many ways, more interesting. Piranhas are opportunistic omnivores with highly flexible feeding strategies. Some species consume insects, seeds, and fallen fruit, in addition to fish and carrion. Others specialize more heavily in predation, but still rely on opportunity rather than constant aggression. Their famous teeth and powerful jaws reveal part of the story. Each tooth is triangular, razor-sharp, and designed to slice efficiently through flesh or plant material. When combined with strong jaw muscles, this dental arrangement allows piranhas to remove chunks of food quickly, an adaptation particularly useful in competitive feeding situations. But teeth alone do not explain the fish's ecological role. The real advantage comes from their ability to interpret signals in the water and respond collectively when conditions favor feeding. Water transmits chemical information remarkably well. Blood released into the river dissolves rapidly, creating a plume of organic molecules that drift with currents and eddies. At the same time, injured animals often produce erratic movement patterns as they attempt to escape. These movements generate pressure waves that spread through the surrounding water, detectable by other fish through a sensory system known as the lateral line. This system consists of a series of microscopic receptors running along the sides of the body, allowing fish to detect changes in water pressure and vibration. For piranhas, the combination of chemical and mechanical signals is particularly important. A single drop of blood does not automatically trigger a feeding frenzy, despite the mythology surrounding the fish. Instead, piranhas interpret multiple cues together. The smell of blood might indicate the presence of wounded prey. Sudden splashing could signal that something is struggling near the surface. Rapid movements of other fish in the area might reveal competition or opportunity. When these signals converge in the same location, the fish become more active and investigative. Seasonal changes in the Amazon strongly influence how these events unfold. During the rainy season, rivers expand dramatically as floodwaters spread into surrounding forests. Vast areas of land become temporarily submerged, creating a labyrinth of flooded trees, vines, and floating vegetation. In this environment, prey animals have many escape routes, and water volume dilutes chemical signals quickly. Piranhas disperse widely through these flooded habitats, feeding opportunistically on whatever resources appear. The dry season creates a very different situation. As water levels fall, rivers contract into narrower channels and isolated pools. Fish become concentrated in shrinking spaces where competition intensifies. Food resources may become less predictable, and animals are forced into closer proximity with one another. In these conditions, signals such as blood or frantic movement carry more weight because the animals interpreting them are already nearby. Imagine a wounded fish entering one of these confined pools. The first sign of trouble might be the irregular motion of its swimming, a jerking movement that disrupts the smooth patterns typical of healthy fish. Nearby individuals notice the vibration through their lateral lines. A faint chemical trace follows as diluted blood begins to disperse. One or two piranhas approach cautiously, circling the disturbance. Their movements are not explosive, but investigative, testing the situation. If the injured animal continues to struggle, the signals intensify. Splashes and vibrations attract additional fish. Each new arrival increases the density of bodies moving through the same patch of water. Competition begins to shape behavior. When one piranha takes a quick bite, the reaction of others can change instantly. The presence of food triggers rapid feeding responses, and multiple fish may converge on the same target within seconds. Yet even in these moments, the behavior remains governed by opportunity rather than blind frenzy. If the prey escapes into open water or reaches dense vegetation where access becomes difficult, the event may end abruptly. Piranhas often return to their normal patterns once the disturbance disappears. The dramatic feeding scenes, sometimes captured in documentaries, typically occur when prey is trapped or when environmental conditions prevent escape. This nuance matters because it reveals how closely piranhas are tied to the broader ecological system of the river. They are not mindless predators, but participants in a network of signals and responses. Injured animals attract attention not only from piranhas, but also from catfish, turtles, and other opportunistic feeders. Birds watching from the shoreline may dive to seize struggling fish near the surface. The disturbance spreads through multiple layers of the ecosystem, each species responding according to its own sensory abilities and feeding strategies. In this sense, the piranha represents perhaps the clearest expression of how rivers interpret biological information. Blood entering the water becomes part of a chemical narrative that travels outward through currents. Movement adds mechanical cues that amplify the signal. Nearby animals react, creating additional disturbance that draws even more attention. What began as a single injury gradually transforms into a shared event within the aquatic community. For humans observing from the riverbank, this chain reaction can appear sudden and dramatic. The water may look calm one moment and chaotic the next as fish break the surface and scatter in multiple directions. But beneath that apparent explosion of activity lies a process driven by basic ecological principles: detection, opportunity, and competition. Piranhas excel in this environment because they respond quickly to the convergence of those signals. Their sharp teeth allow them to exploit food efficiently in crowded conditions. Their sensory systems detect the vibrations and chemical traces associated with vulnerable prey, and their tendency to gather in groups ensures that when food appears, multiple individuals can capitalize on the opportunity before it disappears. By the time the disturbance subsides, the river may once again appear quiet. The water smooths over, currents carry the last traces of scent downstream, and the fish disperse into the shadows beneath submerged branches. Yet, the event reveals something fundamental about life in the Amazon. Injury does not remain isolated for long. The environment itself interprets it, distributing its signals through air, water, and soil. Across the rainforest, each of the animals encountered in this journey responds to those signals in different ways. The jaguar reads scent trails drifting through humid forest corridors. The bushmaster waits silently where panic makes movement predictable. Giant otters patrol rivers that broadcast disturbance across their territory. Electric eels interpret electrical chaos in dark water. Assassin bugs exploit microscopic traces of exposed tissue within the leaf litter. And piranhas respond when chemical signals combine with movement and competition in confined water. Together, they illustrate a single, unforgiving principle. In the Amazon, blood does not remain private. Once it enters the environment, it becomes information, and the forest is full of creatures ready to read it.